And I'm just giving a couple minutes for everybody to get here and get connected and situated. And while we're doing that, if you have anything you want to talk about, let me know. Okay. Okay, so while in the first few minutes of class, what I wanted to do was kind of give you a sense of where we are. This is week 7 of an 11-week class. So wait, 7, 8, 9, 10, 11. So this is one of 5 meetings that we have left. And what I've noticed is that as I've been grading the homework, there's been a lot of missing homework assignments over the course of the last few weeks in particular. Some folks have come and emailed about wanting to try to make some of that up. And so Carl and I discussed this, and if you're one of the students who's missing a whole bunch of assignments, this is the time to turn it around. There's only literally like 2 homework assignments left and 1 project. So we're in the home stretch here, and you don't want something like the assignments, which are worth 40% of your grade, to you know, take you, instead of getting an A, to a B, or from a B to a C, whatever that is. So if you want to talk about your grade and how you can maybe make up some of that work, then we encourage you to visit with us in office hours next week. My office hours are 12:30 to 2:30 on Wednesdays, and Carl's, I was just looking, I haven't got his memorized. If anybody has the site up and wants to share with everybody, that'd be great. Otherwise, I'm just trying to look it up on the announcements as to what his office hours are. Here we go. Okay. He has office hours on Tuesdays, Wednesdays, and Thursdays at various times. So Tuesday, 12:30 to 1:30, Tuesday, 5:30 to 6:30, Wednesday, 11 to 1, Wednesday, 6 to 7 p.m., and Thursday, 1 to 2. And we're both available for our office hours through the STEM Center. So rather than email any one of us, we would like to see you in office hours with regards to homeworks. Okay, what else can I say? I have graded this section's projects, and I want to say that y'all did a great job. All of you who submitted a video that I could watch, really great job. I hope you took a lot away from it. I noticed that only about 50% of the class did the peer reviews. So I wanted to specifically ask if there was an issue with that, or you just didn't do it. If there was confusion about it, I'd like to hear some feedback on that, if you're willing to give that. Any feedback? Okay. Oh, go ahead.
I was just gonna say, I was having a hard time figuring out how to upload my video, because you told me to, and then
yeah, your video, did you, so it was interesting. Your video got, like, the way it was posted, it actually said that a lot of the class viewed it. I was also confused by that. Maybe some of the class could could let us know. Were you able to see her video? Was anybody able to see her video? Okay, that's strange. Anyways, so I'm sorry you didn't get any feedback on your video because I think others couldn't see it, but it was a great video. So I got to see it. And so I was trying to figure out how to do that, how to make your video available, and I also couldn't figure that out. Could you tell us how you produced the video? Was it a YouTube video or was it a Confer Zoom video?
I did a local recording on Zoom, but when I would try and upload it from my computer, it wouldn't let me. Like there's.
So you did a local recording on Zoom. I see. So yeah, I think that we weren't allowing video uploads because they are too memory intensive, and the class has a memory a memory limit. So we weren't able to allow people to upload it. So I think what the issue is on that one then, and this is for future, is that you can't do a local video. You actually have to let Zoom store the video so that you can get a link for it. And if you do a local video, then you need to upload it to YouTube so that you can get a link to share. Does that make sense?
Yeah, that's probably where I went wrong then.
Okay, you didn't do anything wrong. This is all a learning process for us. It's just unfortunate that others couldn't see yours. So if you want to have it so that others can see yours, maybe you could upload it to YouTube and send me a link directly, an email link, and then I can post it for others to do or to watch. Okay, and then I have some more comments here. Yeah, so some of the videos you were asked to peer review, and I apologize for this. This is something that we also are learning as we go along, is that as soon as the videos were due, we needed to check all the links, and some of them, the links weren't working. However, to finish your 3 peer reviews, if you didn't do the 3 that were assigned to you because you ran into a stumbling block on one that wasn't working, you could have viewed any of the other ones that were posted there. So that was also still an option, and many people, there was one, the first video posted, I think, got a lot of comments on it. Again, if you would like to do peer reviews and that's a part that you haven't done, come and speak to me in my office hours or speak to Carl, and we will make it possible for you to make up those points. So that's kind of where we're leaving it right now, is, you know, if this is something you, to use someone else's words, spaced out on and, you know, need to revisit it, then let's talk about it one-on-one next week. Let's look at your grades. Let's look at your whole overall performance in the class and figure out the way forward. Okay, so the opportunity isn't gone. And that's why you can upload your video and send it to me, and it can still get some peer reviews. Okay? Same for the one I talked about earlier in class when there were just a few of us, that was private. We can get you some feedback on that as soon as you make it public. All right. Okay, so this week we're talking about civil engineering, and we have 3 great civil and architectural engineers coming to speak with us. So that's going to be really exciting. I wanted to start out the class with a little overview of like some of the great civil engineering projects that we have been, that have happened over time in the world, as kind of just a preview. You guys have all learned about, oops, wrong way. You've all already learned about what civil engineering encompasses. So, because we talked about that, I think week 1 or week 2 or week 3. I think this class, it was week 2, where we went through the engineering disciplines. Let's see here. Oops. Okay. Sorry, I have to let some folks in from the waiting room. Okay. And the other thing about that is that I also posted 6 short videos for you to watch that go into like individual people who are working in each of these specialties of civil engineering. And I think you can get a lot out of that because some of them are students, some of them are young professionals, and they can give you some more insight into what they do on a day-to-day basis in each of these 6 subdisciplines of civil engineering. So rather than rehash what is civil engineering, I thought instead we look at some great civil engineering projects, and some of them you may be familiar with and some not. And talk a little bit about, you know, some of the things related to these projects. So we all know that civil engineers design, build, and maintain basically the foundation for our modern society. They do the roads, the bridges, drinking water, energy systems, seaports and airports and transportation and infrastructure for all of these systems, as well as for keeping the environment clean. So that's just a brief overview, and like I said, please watch the 6 videos. In fact, I think the follow-up on this is to reflect on the videos, so you will need to watch them. Okay, so, you know, civil engineers have the American Society for Civil Engineering. I think some of you may have come across this in some of the homework assignments that we've done so far. And the American Society for Civil Engineering actually celebrates a lot of creativity and innovation in civil engineering by showcasing some of the projects that have taken place all over the world through their Civil Engineering Landmarks program. And these projects are at least 50 years old. That's one of the criteria. So some of the things I'm going to show you have earned that distinction. Some of them, so I haven't included everything here, but this is a link to their website. And I think rather than click on it, I will insert the link into the chat at the end of this so that you can explore it on your own as well, okay? Okay, so let's start with one of the first ones. And I'm kind of going in chronological order, actually. So this is one of the oldest ones we'll look at, which is the Great Wall of China. It took over 2,000 years to build. It's actually composed of several walls that are built, rebuilt, and merged and expanded to create the wall that stands today. It was completed between the 15th and 17th centuries. Construction actually began in 475 BC. And the purpose of it was to protect China from a group of people called the Huns, who were invading parts of China and Europe. And so they built this to protect themselves. Some facts about it: some of the watchtowers stand 3,215 feet above sea level. The wall reaches a maximum height of 25.6 feet and is 16.4 feet wide in some areas of its base. What is most interesting about this from my point of view, and what most people don't know about it, or maybe you do, let me ask you actually, what is the mortar made of that holds most of these stones together? Does anyone know? Any guesses out there?
Plants, maybe like rice.
Ooh, that's a really great guess. So yes, it's actually made from rice flour, which is truly amazing because not only is it hard to imagine that that would be used as mortar, but it stood the test of time, right? There's a lot of actual work going into restoring some of the areas where it's, you know, eroded over time, but rice flour is what the mortar was used to hold all the stones together. And another thing a lot of people think is true, and let me ask you, can this be seen from space, the Great Wall of China? It's 5,500 miles long. What do we think? Can it be seen from space? I'd rather you speak up than type in the chat, because I can't see the chat and all of your and the screen and everything at the same time.
No.
Right, it actually can't be seen from space. Many people think it can, but it's too narrow to be seen from space, even though it's so long. Interesting. Okay, so that's our first one. Let's look at the next one. So this one maybe not as well known. This is the Aqueduct of Segovia. It is in Spain, and it is actually, let me see, 24,000 granite blocks, 11 miles. It runs from the Fuente Fria River all the way to the city of Segovia, and absolutely no mortar is used at all in the construction of this, which is truly amazing. There are 167 arches that are more than 29 feet high, and in many places along it, you see the double arch configuration you see here. This was named one of those historic civil engineering landmarks in 1999. So the whole idea behind it is it transported water from the river to the city, and believe it or not, it's so well preserved that it's still doing that function today. Pretty amazing. All right, the Panama Canal. So now we're jumping way far ahead. Look, thousands of years. The Panama Canal in 1914. This one we're all familiar with, but do we really know how it works? This is really an amazing system they've built. It is 47 miles long, okay? So that's the width of that little isthmus there in Central America. And it allows us obviously to connect the Atlantic and Pacific Oceans. So it reduced what was a trip around Cape Horn by 9,000 miles. So it used to be that long to get all the way around South America and into the Atlantic Ocean or vice versa. More than 15,000 ships go through here every year. What else can I tell you? It needed more than 60 million pounds of dynamite and 40,000 workers to dig and build it. And they moved enough dirt to bury all of Manhattan 12 feet deep. The way it works is like the photo at the bottom that you see here. Ships are lifted up on one side and lowered on the other. And the total distance they go up and down is 65 feet. Each one of these doors is called a movable lock door, weighs 750 tons, and fills with 52 million gallons of water to raise the ship. That's how they raise it. This has actually been named one of the 7 wonders of the modern world and is also on the Historic Civil Engineering Landmark list by ASCE. It's pretty amazing, right? Okay, let's look at another one. Hoover Dam. How many of you have been here before? Anyone been here and know about the Hoover Dam?
Nope.
No? Has anyone been here?
I went when I was like 4.
Okay, do you remember anything?
No, I just
No. Oh my gosh, guys, this is not far from us. Do we all know where this is?
Again, no.
No, I have a map right there. It shows it, right? It's on the border. It's near the border of Nevada and California. It's actually in Nevada. So what's so amazing about this dam is that it formed the largest man-made lake, which is Lake Mead, which you see on the map here behind the dam, in the Western Hemisphere. Okay, imagine that. The dam itself generates 4 billion kilowatts of energy per year, which is actually enough power for 1.2 million people. And that power is distributed to Nevada, Arizona, and California, probably Southern California, but part of our own state here. Look at this picture on the right. It's almost 690 feet thick at the base. This is the shape of the dam. and it's 45 feet thick at its highest point. It rises 725 feet above the Colorado River. Okay. It's named one of the 7 wonders of the modern world, and it's on our historic civil engineering landmark list that ASCE produces. But it's also named a Millennium Monument, and Millennium Monument means that it is an achievement that has had one of the greatest impacts on life in the 20th century. So it's truly a marvel. And I know in the times of COVID, it's probably not happening, but in normal days, you can actually tour this site. You can, I think that the tour is free, or it costs like $2 or $5 or something. So if you're in the area, it would be really a great thing to visit, especially if you're interested in civil engineering or any type of energy engineering, hydropower, anything like that as well. Okay. This one was made more recently. 1994, I was just trying to do some math to see if most of you were alive when this was built. I was, so I remember it, but I don't know if it's in your early years, if you recall hearing about the English Channel Tunnel, which is also called the Channel, which was made in 1994. It is a tunnel that runs under the English Channel, and it happens to be 31 miles long and up to 250 feet deep. It connects England and France. It's actually the second longest tunnel in the world and contains the longest undersea portion of any tunnel in the world. What's interesting about it, high-speed trains run through it like you see here, and these high-speed trains move so fast that there are valves in the tunnel walls that open and close to vent the pressure that builds up as the trains push through the tunnel. So just imagine that. It actually took 6 years and 13,000 engineers, construction workers, and technicians, and 11 boring machines to build. And I've got a photo, yep, right down here, of a boring machine as it's making the tunnel. And this is what the inside of the tunnel looks like today. And this is kind of how it runs under the seabed. So really, really fun. Has anyone been on this? Anyone been to England or France and gone between on this?
No.
Sorry, I didn't hear whoever spoke after Nick.
I've been wanting to.
Yeah, me too. Yeah.
Things.
Looks really cool. I wish someone in the class had the chance to be on it and can tell us about it. I also want to know about the high-speed train aspect of it, how fast the train goes and what it feels like. Have you guys been on BART that goes under the bay? Has anyone done that?
I have.
Yeah, and so when you did that, did you notice when you hit the bottom?
No, I didn't.
No. Okay, so when I go on it, my ears actually pop right when we get to the bottom of the, I guess, the floor of the bay, and then my ears pop again when we come back up. So this would be really interesting because this is even deeper.
It's been a while since I've been on it, so maybe that did happen. But.
Yeah.
Weren't we supposed to have high-speed trains here in California at one point?
The ones that they were talking about for California were above ground. But yes, there was a lot of talk of a high-speed train between San Francisco and Los Angeles, and there's been a lot of talk of a high-speed train also on the East Coast between Washington, D.C. and New York. I don't know right now. Does anyone know about the status of either of those? Yeah, I haven't heard about it recently, but those are both great civil engineering projects that are in the future, and they're not the only ones. There are high-speed trains being developed all over the world. I think Japan has already got one. I think China might be putting one in. I know that there's the TGV in France that runs from north to south. So lots of opportunities to work on a project like that after you graduate with a civil engineering degree in the next several years, for sure. Okay, let's see. I only have a few more slides. All right, so this, I think I mentioned this tower before. This is the Burj Khalifa Tower in the United Arab Emirates. When we first talked about civil engineering, but I don't think I talked about a lot of the specifics of it, other than it happens to be the world's tallest skyscraper, and at a height of 2,717 feet. It is actually almost a full 1,000 feet higher than the One World Trade Center in New York. Just to give you an idea, and actually down here, I show some comparisons of other really tall buildings that you may be familiar with. And so just to give you an idea of how tall this really is. Anyone know how many floors there are in 2,717 feet? Any guesses?
One of the books I have with me right now is a Guinness Book of World Records that actually has this in it, and I think it's like 163.
It is, you're right. It is 163 floors. Can you imagine riding that elevator? It's probably not one elevator that goes all the way to the top. In fact, I think I've been in the Empire State Building, and I think it was more than one elevator bank that you take. You take different ones to get to the top. But it's kind of scary to think that you're standing up there. There's 27 terraces on this building, so you can, make your way outside and take a look down. It is the tallest freestanding structure in the world. Now, what's most interesting about it is the way it was tested for withstanding the winds. So strong winds are actually a big problem in this area of the world. And so they had to do 40 wind tunnel tests to determine the wind's impact on the building and also on the construction cranes that would build the building. And they built it so that it can withstand winds of up to 99 miles an hour. So this is a problem with all super tall buildings, but they had to do 40 tests to get it right. It took 22 million hours to build, and some of it was done at night to avoid the high temperatures during the day. So really an amazing building. Has anyone been here? Not me. Yeah, not me either. Interesting. Okay. Cool. All right, let's see. What have we got next? Ah, this bridge. Okay, so we're familiar with bridges in the Bay Area. We've got quite a few of them. This is the, I'm going to say it wrong, Qingdao Taiwan Bridge, I think. Qingdao might be how it's pronounced. This was completed in 2011. Thank you for that comment. We do have a lot of field trips to do after COVID, and wouldn't it be great if we did a whirlwind world tour of like all of these sites and all the other ones? That would be so amazing. Okay, so this bridge completed in 2011. Sorry, give me a moment. Okay, sorry about that. I was interrupted. Okay, so this, any guesses on how long this is? So let me tell you, because I've been riding my bike across the bridges. The Richmond Bridge is 7 miles, and the Bay Bridge is 5 miles, I believe. Oh, just to Treasure Island. East Bay to Treasure Island is 5 miles. How long do you think this bridge is? And don't look it up in the book. Just take a guess. Any thoughts?
12 miles.
12? That seems like a big bridge. Any other guesses?
As long as the Great Wall.
Wait, well, how long was that? 5,500 miles. No, it's not 5,500 miles. Any other guesses? What have you got to lose? Just say a number.
7.7 miles.
How much?
7.7.
7.7. Okay. It is 26.4 miles long. Okay.
27.7.
Yeah, it's a really long bridge. Now, there are actually people that are afraid of driving across bridges. There's a word for it, which I don't remember, some phobia. And it actually exists. Can you imagine being on a 26-mile bridge? Kind of crazy. So it was completed in 2011. It used 450,000 tons of steel and 3 million cubic yards of concrete. It is actually built, this is what's most amazing about it, it is built to withstand typhoons, which is what they call hurricanes in the Pacific, earthquakes up to 8.0 on the Richter scale, and an impact of a 300-ton vessel. So like a huge ship ran into it, it wouldn't break. It took 4 years and 10,000 workers to build. And this map kind of shows you where it is in China. Pretty amazing. Okay. I'm sure you guys have heard of the Palm Islands in Dubai. Has everyone heard of this? I don't have a date on it. I feel like it's still being built. But anyone know why these islands were built? I have one person who's heard of it. How about some guesses as to why would someone need to build islands in the world when we have all these islands?
I don't know, housing?
Housing, that's a really good guess. It actually isn't housing. Can you believe it? They didn't build them so that they could house more people. Well, they did in a way, actually. I should take that back. But it wasn't permanent housing. This is all because the sheikh wanted to increase the number of tourists to his kingdom, I guess, to 15 million, and he didn't have the land to put 15 million tourists on. So he built these islands. Now, these islands can be seen from space. And the smallest of these is actually the biggest. How's that possible? It is one of the biggest man-made islands in the world. There's 3 of them, so there must be 3 of the biggest man-made islands in the world. They are artificial. They were made from reclaimed, I guess, what am I trying to say? Rock, sand, and limestone. So all of that was like from construction projects that had, they'd torn buildings down and stuff like that, where areas where they dredged the bay to get the sand. They used all of that to build up the island. So it wasn't taking new stuff. It was using stuff that was already in use once before and using that to build the islands. It's actually one of the most controversial engineering projects ever because, again, why would you want to build an island when there's so much land in the world and it's all just for tourism? It's also all made from natural materials like rock and sand that were already existing too. So reclaimed rock and sand that would have been thrown away or made in a pile somewhere else was instead put in the water. Many people were concerned about the effects of, changing the seabed and the dynamics of the waterway there. But I think engineering studies have shown that the sea life wasn't as impacted by the building of these islands as they thought it would be. So that's been good news. The whole purpose of this edge right here is a breakwater to prevent the winds, those horrible winds we've already talked about, from creating huge waves that then get, would hit any of the buildings and structures here. So they had to create this breakwater. I think that's all I had to say about this. I think it's really, and did I say you can see it from space? I think I said that. So it's pretty amazing. Okay, so last one. This is a really interesting one. Actually, I think I went back in time for this one, but I wanted to talk a little bit more about this one. Anyone been to the Citicorp building in New York? Anyone? No? Okay, well, this building has a very interesting story, and actually I think it's one that you may be able to relate to as students. It's a good story. So this building was built, I think it says 1977. It is 915 feet tall. In 1977, it was the 7th tallest building in the world. So just to give you an idea, we've already looked at the tallest building in the world. It has 59 stories and it's made of steel. Look at the bottom of the building. What do you guys see? That's somewhat unusual.
It has a smaller base than the rest of the building.
Well, yeah, exactly. And it's not really a base, right? It looks like it's on stilts. Do you see the 4 pillars at the bottom here? So this was an engineering challenge from the beginning. What happened was that the northwest corner of where this building was going to sit, of the proposed site, was already occupied by a church, St. Peter's Lutheran Church. And the church allowed, I guess, had to give City Corps the permission to build the building, which they did, but they put one condition on it, and that was that the church wasn't going to move. It had to stay on the corner, and it had no connection to the City Corps building at all, and it had no columns or any sort of supports going through it. Okay, so basically, the way they designed this building then was to put it on 4 massive columns that you see in this photo here, rather than in the corners. And this is not a traditional way of building a building. Usually the supports are in the corners. So these stilts, which is what they're called, actually are 9 stories tall. And this allowed for the church to remain, which I don't think we see in the photo here. So it must be on the opposite corner from where this is taken. What was I saying? Oh yeah. And the church is kind of sitting under the base of this building here, so that the church must be behind and about this tall. The architect of this building was Hugh Stubbins, but the person who gets the most credit for this building was a structural engineer named William Lemasurier. And I have a video that he has made that I will publish when we're done here. This was a cutting edge design for its time. And everything seemed fine. It opened up, people moved in, and it was in use until one day, Lemasurier in 1978, a year after it opened, got a call. And the call was from an architectural undergraduate student, an undergraduate architectural student. Her name is Diane Hartley, and she's shown here on the slide right here. She had something very important to say. She told him that she believed the building could blow over in the wind. And he actually was like, kind of laughed it off and said she didn't know what she was talking about. But then he kind of thought about it. And what had happened is that he had done a lot of work on making sure that the building could withstand winds. And he had looked at the perpendicular winds that strike the building at the faces that cause the greatest strain, and had made sure that this building could withstand that. But what he had not looked at was what's called quartering winds. And these are winds that strike the building at the corner. And Diane Hartley was studying this building. She was actually working in it and studying it, and she realized that this building, the way it was built, wasn't built to withstand those quartering winds, and that's what she told him. And so he went back after receiving this phone call, and he actually checked his math and found that she was right, that the building could not withstand any winds that came towards the corners. Was there a question? No question? I think Francesca, I'm going to mute you because I hear some static. Oh, thank you. Okay. So immediately he was just like so alarmed, and he's like, what do I do? I keep hearing, Francesca, do you have a question? Because it's kind of muffled.
Francesca, I'm going to mute you. I hear you just like so.
I couldn't understand. Do you want to type into the chat what you're trying to say? Okay, I'll look at the chat. I don't see anything there. Go ahead and type into the chat, Francesca. Oh, okay, great. It might be there. My computer's overheating. Yes, I think that is what's happening. This is being recorded, so if you need to step off, it'll be videotaped. Okay. So anyways, so what went wrong basically is that, you know, you all watched that video when we talked about the engineering design process and a failure that had happened of that bridge. And if you recall, the failure of the little people bridge where it had fallen from its supports was that they had used these bolts instead of a new kind of securing system, fastening system that the engineers had designed. So when the construction workers went to make that bridge, they used normal bolts rather than what they should have used. And actually the engineers signed off on it. So without looking at it, but then that led to that failure. Well, this is something very similar as well. So what had happened is that when he went back and looked at the way the building had been built, he saw that the joints on the chevrons, which are the diagonal pieces, and I don't think either of these photos show it, but within the building walls are these diagonal beams that run. He found that the bolts, that the joints on that were bolts and not welds, and that was a huge problem. The actual builder of the skyscraper hadn't been aware that they needed to account for the quartering winds, the winds that hit on the diagonal, so they used bolts instead of welds. Now, he had designed the building so that it had a huge mass damper. This is what this is right here. Which was the first time, one of the first times this has been used ever. And the mass damper actually helps with the building to sort of sway with the wind so it doesn't topple over completely, kind of to absorb the wind. And so you would think that, you know, if it's okay with the bolts because you've got also this secondary mass damper. But the thing about the mass damper is that it runs on electricity. So if the electricity goes out and the quartering winds hit the building, then you've got a catastrophic failure waiting to happen. So what he had to do, well, he ran some numbers and it turned out that these quartering winds actually have an average span of about once every 16 years that they hit the city. So for every 1 year it's standing, it has a 1 in 16 chance of falling over. And it just so happened that there was a hurricane, you know, it was going to be hurricane season. So he went immediately to the city core people who owned the building, told them what had been found, and they proceeded to retrofit the building. And how long did that take? I think it took, I don't remember. No, 3 months. It took 3 months for the construction crew to go back and weld steel plates over each of the bolted joints within the building. What's interesting, so I've given you this whole story and you're like, wow.
Did they
okay.
take out the bolts or just weld over the bolts?
They welded over the bolts and they had to evacuate the entire building for 3 months and they didn't tell anybody why. This is what's fascinating about the story. In fact, for 20 years after this building was standing, so this is in the first year that this has all come about, right? It was built in 1977. Diane contacts him in 1978. Takes them 3 months to fix it, weld every joint. I would imagine tear into the walls and all of that. And then for 20 years, they told nobody about what had happened. Nobody knew why they were evacuated for 3 months. But the story gets even more fascinating. So while the welding was happening, of all things, a hurricane called Hurricane Ella was on its way to New York. And luckily, the hurricane veered away from New York. But if it had hit New York in that moment, it is quite likely the building would have fallen over because it wasn't done, basically. There's a 30-page document that outlines the structural mistakes of this building. It's called Project Serene, and the Serene is an acronym that stands for Special Engineering Review of Events Nobody Envisioned, which is quite funny. Oh, it was 6 weeks into the repair that Hurricane Ella was headed for New York, and only half the repairs were done. Let's see, yeah. So the other thing about this is that because of his swift action, despite putting his reputation on the line, you have to realize he was the chief structural engineer and the building was built. And he went back to Citicorp and said, look, there's been a major problem. And Citicorp, because of that, actually covered $6 million of the $8 million it cost to do the repairs to the building. And his insurance, which was only up to $2 million, paid the other $2 million. So this is, this is like one of the exemplary engineering ethics examples where an engineer learns of his mistake and goes back and corrects it before there's a catastrophic failure that could impact millions of lives, hundreds of thousands of lives. I don't know, thousands of lives. I don't know how many people were in this building or in the surrounding buildings. Imagine if it took one out. So engineering ethics is coming up actually on your, in this class, it might be next week or the week after for you guys. I think it's next week with Carl. And he may mention this engineer as having exemplary ethics. Can you guys think of any examples, recent examples, where engineering ethics has come into the discussion in a bad way?
Can I say something?
Yeah.
It's not answering your question, though, but it seems that he may have had good ethics in this case, but I think he must have known on some level at least that he would have been protected quite well. And he was already had such a high standing in his profession that, of course, if it didn't go over well, then his career could be basically screwed. But he probably knew on some level that it could have been paid for, because it sounds like he really lost nothing. You know, he didn't even lose any reputation. In fact, he's probably seen as some kind of honest hero out of it. It's kind of
he is. He is now seen as a hero, but at the time
but he didn't pay the price.
He didn't.
Yeah.
Well, what is the price? The monetary price?
Yeah.
Well,
Literally.
but someone could. He wasn't the one that discovered the problem, so someone could question his own. What am I saying? His own ability to design buildings, right? He's not the one that figured out the problem. This undergraduate student did. So his reputation was still on the line. Actually, because he came forward, he is now seen as a hero, and you can look up his name. He has an amazing website. He's worked on so many buildings. It's probably one of the mistakes in his career that jump-started his career into something he never would have imagined. Yes. But if he hadn't have come forward, right, he actually did blow her off, essentially, when she first called and said, you don't know what you're talking about, you're just a student. Think of what might have happened, right? So there's kind of a few different ways to look at it. And in fact, he never even got her name. It was only after the article was published, after 20 years, that the story came out, that she came forward and said, I'm the student. So he owes her quite a lot, actually.
I agree with that.
Yeah. What was my question? I forget. Oh,
Other situations.
other engineering ethics situations, just to give you a preview, a taste of what's to come next week. Any thoughts on that? Okay, well, I encourage you to give it some thought. One of our speakers should be here. Let me double check if they're here or not.
I think Volkswagen had a recall on some of their like, what was it, 2016 Jettas or something, and they had to recall like a lot of them.
Yes, they did. That's one of them, definitely. Okay, give me a moment, guys. I'm just gonna pause. I think our speaker is trying to meet with us, so let me try and get her on.
Cool. Well, hello everyone. So I went to Cabrillo, and at my time at Cabrillo, I just kind of dove into whatever I could get involved with, and really that was to try and get some engineering experience, try and have just college experiences, and more importantly, to network. Like where I've gotten to now, I can say has been mainly because of my networking and being able to connect with different people. I transferred to San Jose State, and while I was there, I was a part of, they have their engineering abroad program as well, so I did that there. I guess career-wise, while I was at Cabrillo, I was working at the Monterey 1 wastewater treatment plant Marina. And when I transferred to San Jose State, I was working for the County of Santa Cruz in Public Works under road design. I also had like second jobs to, make ends meet. And I'm now in Davis, just living my life.
Can you mentioned, Khalifa, that networking was a big part of what you took away from Cabrillo, and I know that some of the students had explored or mentioned networking as something they were interested to learn could be done virtually. Could you talk about some of the ways you networked?
Well, this was all pre-COVID. My first experience with networking was actually through the Engineering Abroad program. Joanne set up these presentations at different organizations. And in these organizations, you have the opportunity to meet with other working professional engineers in your local area. And so I found that to be very valuable. And from that, I ended up joining one of the organizations, APWA. It's the American Public Works Association. And most organizations tend to have a student chapter on campus or a young professionals type of subgroup that's geared more towards young professionals just starting and students. And you can find that kind of just all around. I guess through school, you'll meet people who are like, oh yeah, and at San Jose State for civils, ASCE is a huge organization. And they're super heavily involved in making sure that their students graduate, being able to connect them with potential mentors, different internship opportunities, even scholarships. And yeah, I will admit I'm not the most social, I guess. I'm a little introverted. And I have a couple of other friends who are kind of like, oh, really shy. I've never done any type of engineering thing. I don't know what to talk about with these people. And really everyone is understanding that you're a student, you're just starting out, and they're really excited to help you just grow as an engineer, both academically and professionally. So just pushing yourself through to try and talk to people. Just ask them, what is the project that you're working on? Oh, I saw you gave this presentation on this certain topic tonight. Like, tell me a little bit about that. And for sure have a genuine interest in the conversation you're having. That's,
Yes.
you can tell right away.
You've been to Cabrillo, you've gone through the transfer process. What advice do you have for these students who are literally in some of the first semester at Cabrillo?
When Cabrillo, there is no place like Cabrillo. Everyone, well, from when I was going there, it was super tight knit. The STEM center was new, everyone was excited, and when you transfer, you may or you may not go through this period of, I guess, grieving, because it is different. And when you transfer to the four-year universities, sometimes it's a little more self-driven, and you have to be the one to put yourself out there, to ask your professors for help, to join an organization or a student club. Transferring really is what you make of it.
Okay, great. I want to let everyone know that they can ask questions themselves or type into the chat, and I'm happy to read those questions off. Can you talk about some of the work that you've done? You mentioned you work at APWA. Like, what was some of the favorite stuff that you had done while you were working at those organizations?
Well, do you mean work or through like because APWA is an organization? And so
I thought you said you joined you went to work there. Sorry, I got confused.
So I was working at the County of Santa Cruz.
That's it. Okay.
And yeah. When you're looking for internships and for jobs, whether it's the exact job description that you're looking for, or whether it's something that you're thinking, I don't know if I really want to do this, apply. Because when I first started at the county, I applied for a position that was described as an engineering aid position. And when I went to the interview, it actually wasn't engineering at all. It had to do with a program for sustainability. And so went in, had nothing to do with engineering, and then 2017 came with the winter storms, and it wiped out a lot of our roads in Santa Cruz County. And through that, I had already been there for about 3 months, and so I had talked to kind of everyone around and was getting familiar with people. And the road design crew knew that I had an engineering background and that that's what I was going to school for. So they were able to pull me from what I was doing and put me into this engineering aid position, where that really kind of, I was working on filling out federal forms for Caltrans and for FEMA to make sure that we got funding for these projects to make our roads better. I learned the process of proposals. I was writing requests for authorization packages.
Wow.
And so it's a lot of kind of behind the scenes paperwork that is part of engineering. Like when I first started engineering, I thought, okay, engineering is all about design, because you're taking these classes, you're learning about all these design techniques and kind of different basic engineering principles that have to go into a design. When you get into the workforce, if you're not a design person, don't worry, there's other engineering positions that don't have to do with design. The longer I was there, the last couple months that I was at the county, they actually gave me my own project, a small project, but my own project where I did get to work on design and work on the project from start to finish.
Wow. And well, that's really great. So how long were you there?
I was there for about 3 years.
Oh, wow. Okay.
Yeah.
So what are you doing now?
Plans
now?
Now, I'm actually not working in engineering. I moved up to Davis with my boyfriend, who is going for his PhD in mechanical engineering.
Oh.
So we moved up here, and I'm working at a flower shop as a delivery driver, just kind of taking a break and just working on my mental health and just getting settled.
Do you plan to do a graduate degree, or are you looking for full-time work in engineering still?
I'm thinking about graduate school. I know I still have one more design class that I need to finish, and so once this class is over, I'll start looking for full-time engineering positions. And as far as grad school, I still kind of toss between, do I want to get a master's in civil engineering, or do I want to get an MBA in business admin? Just because trying to figure out what exactly I want to do with my career in the long run. Business is a very popular master's to get for engineers, especially if they want to get into management positions and not necessarily into design.
That's a really interesting take, because I think there would be a lot of students here who may feel the same way, that they want to do a business degree after engineering. Have you looked into programs that might be good for that?
I was looking at San Jose State, but I'm not there anymore. So yeah, I hear Sacramento State has a really good MBA program, but it's still something I need to look more into.
Okay, so are you still a student at San Jose State?
I'm still a student with my last design class.
Oh, okay, yeah, that's great. So when were you at Cabrillo? When did you leave Cabrillo?
I was at Cabrillo. For I think 8 years.
Oh, wow.
I was there for a really long time.
I hope you took advantage of everything Cabrillo has to offer in that time.
I tried, yeah.
What was your favorite thing at Cabrillo, so that these students can go seek it out?
Really, I have to say the engineering abroad.
Oh, the engineering abroad.
The engineering abroad was great.
So you guys went to Guatemala. What did you work on? What was your project there?
Well, just before I get into that, so Clayton, my undergrad is in civil engineering. And some people, they get an emphasis, whether it be geotech, water resources, environmental, transportation, or
structural. Yeah.
Yeah, I actually didn't have an emphasis. It was just purely civil engineering for my undergrad. And so for the engineering abroad program, we were the second group to go there. And our year, we had 3 different projects. And so the project that I was a part of was connecting their already existing kind of tank to just digging out that line to lay down the piping to connect it to the other tanks.
For water or sewage, or?
It was a water, yeah. It was a rainwater catchment system.
Oh, rainwater catchment system. Oh, very cool. How long were you there? A week?
We were there for 2 weeks.
Okay. And how do these students get involved in engineering abroad? Is there a class they have to take?
So engineering abroad is a class and a program. You sign up for your class where you, in the fall, where you have like preliminary meetings weekly. And then you go on your 2-week program. And when you come back, that's when the real fun begins, personally, I thought, because you focus more on, I guess, kind of like the business side and like the formality of creating presentations and presenting your work to different organizations.
Oh, so is it a year-long program essentially to be in the engineering abroad
program? But the part where you're actually in Guatemala it's 2 weeks. Yeah. And
wow.
So you do have to apply for it. And this is the same thing like the engineering abroad over at San Jose State. Most engineering abroad programs you have to apply for. and you'll go through an interview process and they'll select who they want.
Did you do the engineering abroad at San Jose State as well?
Yes.
So where did you?
It was called the Global Technology Institute, I think. Yeah. And so that one's a little different just because it was an international program. So it's whereas like Cabrillo, it's just Cabrillo students and you all go there together, you learn together, you come back. San Jose State, it's a part of an international program. So there's 2 schools from the USA, but there's 11 other countries who are all part of this program. And so the students who are selected to be a part of that program, they meet up our year. It was in Taiwan.
And what did you do in Taiwan? What was your project?
It's split up between research and business. I went down the business route, and we meet with different kind of like entrepreneurs, and we learn the business model and how to start a business from start to finish.
That is so cool. Did these trips cost you money, or were they sponsored, I guess?
So at Cabrillo, Cabrillo was really great because there's different opportunities for you to fundraise, and Joanne is like busting her ass trying to get all of these funds from different local companies. Sorry, excuse my language. And so most of the trip is funded for a lot of the big ticket items. When our year went, we were responsible for covering our airfare, and that we were able to raise as a group through fundraising, through like small little raffles and stuff throughout the school.
How about to Taiwan? Did you have to pay for?
Taiwan, yeah, we did have to pay for Taiwan.
Okay, so not only do you have to apply, but you also have to raise your own money to send yourself there too if you get in.
Yeah.
Yeah.
I'm sorry, I'm like, I can't remember if we paid for Taiwan or not. I know that they did set up, in both occasions, room and board was set up, and meals were also included as well in like your whatever you pay for.
So at San Jose State, for all the students who are transferring, does that opportunity happen in your last year, or because you get there sort of as a junior, right? So do you apply during your junior and go as your senior?
Really, you can apply either way. It just they just want to make sure that you're going to be there full time as a student this semester coming back from your
that's the requirement. Okay. Very cool experiences that you've had.
Yeah.
Does anyone have questions for Khalifa that they want to ask?
Is there some kind of grant for the Guatemala trip?
What you mean in addition to the fundraising?
No, like, I don't know, a grant. I don't know any other word for it.
I think she said that they had to raise their own money for that.
Yeah, Cabrillo does provide funding to cover a lot of the cost, but students were expected to fundraise, or there was the year coming back, the next year's group, there's some people who didn't take part in the like team fundraising and decided, you know, I don't have time for that. I'm going to work my job full time and just save my money for my job. So if you have a job where you can save enough for your own portion of it, you can do that. If you don't, you can also fundraise.
Oh, I see. So they have like some kind of program for the fundraising, so you can pay your own way, like work for it.
Yes,
Okay.
There's the Engineering Abroad program, and then there's the Engineering Abroad Club. And so when you're in the program, they encourage you to be a part of the club because the club is really the entity that helps you fundraise for your portion of the trip.
I think we have one last question because then our next speaker has joined us as well. And I think the question was on these trips that you took for engineering abroad, were you able to go out and see any of the sites while you were there, or were you working the whole time?
So for the engineering abroad program at Cabrillo, it was a pretty full day. We were able to go and sightsee on our own. But that changes from year to year. There was other years where you didn't have much free time and you kind of just stayed together as a group sightseeing. Yeah.
Okay, great. Well, thank you so much, Khalifa, for being here and sharing your experiences with us. It was really great to meet you.
Yeah.
Good luck with your finishing up your degree. It's so exciting.
If anyone, I just wanted to...
Yeah, please.
If anyone wanted to get a hold of me, ask any more questions, my contact information, KhalikaTDiaz@gmail. If you looked at my LinkedIn, here's my random picture that's there. But yeah, I'll share this with you pretty so that you can pass it along.
Yeah, or you could paste it into the chat. That would be great if you just paste your email address or your LinkedIn connector into the chat.
Okay.
Great, thank you.
I wanna ask one last question because it just came to mind. Is that okay?
Yeah.
Oh, okay. So LinkedIn, is that still a thing? Is that important for engineering professional or any professional, or is that just kind of hype? Because I don't know anybody with a LinkedIn really.
It depends. Have a basic LinkedIn setup already. Like at least have one set up whether you use it or not. I don't necessarily use that to network. Some people all about it. And the people who are all about it, they can find my LinkedIn.
Okay.
Okay.
All right, thank you, Khalifa. And I think, yeah, our next speaker who's joined us, Dave Campbell, may want to expand upon the LinkedIn question. And I certainly am willing to give my 2 cents at the very end of class today as well on that. David Campbell is here. He also studied at Cabrillo. He actually first started studying art and then moved to engineering, and he transferred to Cal Poly and graduated with a degree in civil engineering with a structural specialty. So I'll let Dave talk to you all about his career path and you know, what he's doing now and how he got to where he is now. Dave?
Thanks. Yeah, sounds great. I'm going to share my screen here a little bit. So as Preeti mentioned, I'm both I sort of took a very circuitous path to where I'm at now. I started as an art student, did engineering at Cabrillo, ended up transferring to Cal Poly, and then I worked as a structural designer and also in structural forensics for a couple of years. And then I went back and did my graduate degree in architecture. And now I'm a project manager at a firm that does integrated structures and architecture. So we don't really just do both. We really take on projects where we can express both elements simultaneously. And so what I thought I'd do, you know, for the next couple of minutes is just try to explain sort of what that means, you know, how you can kind of merge these things in the context of some of the work that I've done. So to begin, if I can get my PowerPoint back, let's see, there we go. This may not look like the masterwork of architecture here, but you know, how many of you guys, well, I can't see your hands. This is sort of an in-person question, but most of us have eaten pizza, right? And the question is how do we eat pizza? Yeah, thumbs up, great. So some of you have eaten pizza, that's great. You don't just sort of grab it at the back of the crust and let it sort of droop down your hand. You fold it, right? Like a little bit of a taco, especially if it's like thin, you know, New York style pizza. And you're actually using a structural principle there. You're using a principle of virtual work or virtual depth rather. So the pizza is acting as if it's really thick at the back end here, where we folded it a little bit. And we use the same properties for paper airplanes, right? The idea here is that through geometry, rather than strength of materials, we can establish some interesting form and behavior. So I keep losing my advance, there we go. So we applied this directly in this house that I did with Fujian architecture in San Francisco. And we applied it to this stair. And so if you guys are familiar with like San Francisco Victorians, they're really narrow and they're really deep. So they're kind of long, deep, tall houses. And our main goal was to bring a lot of light and air into this space. And so, you know, we still needed a staircase, which take up a lot of room. So the goal was to use folded plates, the same principle of folding pizza or folding a paper airplane, to be able to use perforated steel, about 1/8 inch perforated steel, which is really, really weak. But by folding it, we gain a lot of structural stiffness. And we create not only a space that's expressive, but also that allows light to penetrate deep into the house. So this idea of integrating a basic structural principle into a spatial quality is something that's really sort of fundamental to my work. So this is a bridge we have in Ohio that just opened right before everything got shut down for COVID, just in March. We actually, we're just about to fly out there for our grand opening of this bridge, and everything got shut down. So I actually haven't seen this finished yet, which is too bad. But with this bridge, we started in a similar way. We started from sort of basic structural principles. So with the suspension bridge, we're supporting it on a central tower. And we have a lot of compression, which is this leftmost diagram here. So a lot of compression is carried by this tower. And then in order to pass the bridge deck through, through the tower, we let that compression split into two forces. But what that does is create thrust. So this is sort of like a roof of a house. It wants to push the walls out. And so what we did was we actually tied the bridge deck. We tied the tower back together with the bridge deck. So we resolved the thrust internally. And that's what allowed us to end up with a bridge deck that sort of flies through this eye of the needle of this central tower. And as we go from left to right, you see how we sort of sculpt those forces. So there's a smooth transition from the vertical compression slowly into the lateral and then back into the ground again. With these projects, we have a really heavy use of digital design. So a lot of integration between modeling and engineering, modeling and architecture. And the reason why this is so important is, as you guys are thinking about, how you proceed in your careers, rather your education, what kind of tools do you need in that toolkit? And to be a successful engineer, you don't necessarily have to be able to do sophisticated 3D modeling, but it certainly helps. It opens up a whole nother avenue of form that you can experiment with. So for my practice, we integrate really heavily with our digital models. So, we have a very complete 3-dimensional model. The diagram here on the right sort of shows how that model is built up. And that model is integrated directly with our structural analysis software. So that way we can visualize the architecture 3-dimensionally before we build it, which helps us to raise the money that we need in order to actually build these things. And we can use that same model to also do the structural analysis to figure out construction details and so on. And so this is a time lapse of the construction of the bridge. There's a lot of kind of fun stuff about this, but one of the things that I really loved about this project is the tower itself is a very complicated form. And what they used was actually these sort of press molds that they use for highway bridges. But instead of just using the sort of standard AASHTO shapes, they actually milled CNC blocks within there. And so, they were able to get very, very close to our original design intent of this very complicated structure. And so here you can see they've got the cables all in place and, wrapped it up. And the total construction time, it ended up being close to 3 years. It should have been about 2. But the lead time for the cables, this is probably not super relevant for this class, but the cables are a specialized thing. And so there was, just because of construction scheduling, we sort of had the site essentially laid down for 8 or 9 months. And that's another thing that's really important when you're designing, is to think through what's the critical path? What are the things that have to, go in place and in sequence in order to get something done on time? Because it's very expensive to shut a site down for, several months with nothing happening. And then there's the completed bridge, open for people to go out and be responsible, but still get out into some public space. One of the things that's kind of fun about this project is it's become a place where people do wedding proposals. So on like Instagram, we see a lot of photos of people, doing their photos for their engagements, which is pretty fun.
It's in Ohio is the question, but I have a question for you. So were you also involved in the process to put the bid for this together? Like, how did that part of this process happen where a firm in Emeryville is building something in Ohio?
Yeah, so we also have an office in Chicago, and that's actually part of it, is that we have sort of a national presence. The other piece of it is that we have a reputation for this type of design, and so we get brought in, or we do a lot of competitions as well. This is actually a competition that we won, and then went all the way through the design process. But when it comes, because we're pretty small, when it comes to the actual delivery of the project, we almost always will bring in another partner. So either we'll have a local firm, or we'll have a firm that has a local office. So in this case, T.Y. Lin was the company, which is a huge international firm, and they're the what's called the engineer of record. So we're the design engineer, and we're the architect of record. They're the engineer of record. So they actually take responsibility for the final structural engineering, and for also like walking the site and making sure that the rebar is being placed properly and everything else.
It's a beautiful bridge.
Thank you. Yeah, we're very proud of this, and it's still, as I said, recently opened, so it's still kind of in that nascent stage where I'm excited for things to hopefully get back to normal, where we can actually get out and walk across it myself.
It needs a ribbon cutting for sure.
Yeah. It was really disappointing. We actually had a whole like fireworks show set up and everything, so it was going to be this big extravaganza, because this actually is very important for the town as well. There's a whole new side of the town kind of behind the image, and then we're looking at the old portion of the town, and so this really is the only stitch point between those two districts. So for the city, this is part of like a $3 billion redevelopment of the eastern bank of the river.
What part of Ohio is this? Is this Cleveland?
It's in Dublin, which is just outside of Columbus. So
okay.
yeah, pretty smack dab in the middle.
Right. Yes.
So I'm just curious how it works. Like how there's the cantilever support on this side, but not this side.
Yeah, so
and
the way that
the
this
other side it's opposite. It's really cool. Is it due to the curvature? But like, how does that work?
Yeah. So this is a great question, Clayton. I think that was Clayton drawing, maybe, is what it was said. Yeah. So basically this is a very unique structure. This is the only reverse S single suspension bridge in the world. And basically what ends up happening is it looks like it's cantilevered out on the back end, but it's actually not. It is connected, but it's a slip connection, so it's able to move freely. So what ends up happening is that curvature, and without getting too deep into the technical aspects, the curve is balanced by the single-sided supported cables. So basically the bridge is curved. It wants to sort of tip down toward the river. Let me pull up my drawing tools here so I can not just gesture at you. There we go. So the curved bridge wants to tip, and this one wants to tip the opposite direction.
Oh, so it's balanced.
Yeah, and we have basically the cables are also, I don't know how well you can tell from this photo, but the cables change their angle depending on where they're at. So what they do is they hit these little plates, which pushes them right through the virtual shear center of the section, which means that as this thing wants to twist, it's basically being supported through its sort of virtual centroid. And we do that through the bridge cross section, deck cross section, this sort of box girder that's down below. And then also, as you said, balancing between this side and that side. So
So it has like a triangulated underside.
Yep, exactly.
To balance out that, to transfer that shear value.
Yeah, that's right. It's yeah, shear and torsion. But yes,
yeah, that's the one. I always forget about torsion, but that it looks like it wants to turn like a screw, but it's not somehow.
Yeah, and there's a lot of other kind of weird things about this bridge, which I could probably just talk about for the next couple of minutes, but I'm gonna move on if that's all right.
Okay. Sure. Thanks.
We can always come back. I'll talk about this bridge until you guys are all sick of hearing from me.
I think what would be really interesting for these students to hear about is you have art, you have engineering, you have architecture. If someone wanted to follow your career paths, if they were building something as beautiful as this, do you need all three of those like specialties, or how does that work?
Yeah, that's a really great question. So I would say don't necessarily follow in my career path, even if you want to work on a project like this. And the reason why I say that is because it's such a unique combination of skills that it doesn't really fit very well into a lot of business models. So I got pretty lucky in the firm that I'm working for. My boss is also a dual, the firm principal, and then actually most of the people who work for us are also dual master of architecture and structural engineers. But the art thing is fun. That's how I can get involved in representation and formal balance and understanding from sort of an abstract perspective how these forms should go together. And then the engineering helps me figure out how do you actually do this, and then the architecture is how you detail it, how do you market it, how do you construct it. So with that, it's a very long path, and for me, because I went art and then engineering, and then I worked as an engineer for a while, and then I went to did my master's degree, and now I'm kind of in this. It's one of those things where you're laterally moving in the industry, so it's not quite so much of like a clear pathway. With all that said, if you're interested in architecture and structures, or art and engineering, or art and architecture, there are homes for that type of educational background and skill set within other companies. So, for example, Arup really likes their engineers to have some architectural background, even if it's just a couple of classes or some ability to sketch and that has to do with sort of their ethos, how they work. They at least in their structural portion of their company, it's about being able to quickly, hand draw things. Actually, let me jump forward really quickly. Oh yeah. So for example, and this is another bridge, I'll just talk about bridges all day. On the left-hand side are some of my initial sketches of how the assembly is gonna go, and then our full model. And then, here's another collection of drawings, and then a rendering of the finished bridge. So what's nice about being able to hand draw is you can not only work out your structural system, doing your calculations of how big does the plate need to be at a given spot, how are you transferring forces across a particular node, but also, where what is the sort of presence of that detail? How's it going to feel? What is it going to look like while you're there? When you're doing engineering, to be an engineer that everyone wants to work with, engaging in the process is so important. So not just treating it like it's a problem to be solved and then you're done, but rather being committed to whatever the vision is for that particular project is really important. And then Phaedra, who you'll hear from in just a second, just put a little bee in my ear. The other thing that's worth knowing about is there are a couple of programs in the country that are architectural engineering programs. So the first one is at Cal Poly, and it's an excellent program. It's housed within the College of Architecture rather than the College of Engineering. And if I would have known about it, or maybe known more about it before I went down to Cal Poly, I probably would have gone that direction, because you get actually more structural engineering experience And you also get some architecture studios just to kind of, understand how buildings are being designed, and then how you as an engineer will integrate that process. And the trade-off is you have less like water resources classes and environmental engineering and transportation engineering, all the other things that make up a civil engineering degree. You're taking those classes and doing additional structures classes and then classes in architecture. So if you're interested in this type of thing, I highly recommend checking out architectural engineering. Kansas State also has a really good architectural engineering program, and there's a handful of others throughout the country.
And what kind of software are you using to make these, the different images you've shown us? Like I see sketches, I see this, model, lifelike model, and then you also had something that looked like CAD drawings in there too.
Yeah. So with this, what we're looking at right now, the modeling program that we use is primarily, I would say, is called Rhino, which I don't know if you guys have heard of or not, but it's actually originally designed for boat building. Architects really love it because it's very freeform. You can kind of make any geometry you want, and it doesn't, like Revit knows you're making a building. So it's forcing you into these specific, this window is a window and you can't do anything about it. Whereas Rhino is kind of like, I don't care what you're making. If you're making a lamp or a unicorn, it doesn't really matter. It can handle kind of any type of geometry. So Rhino is really good for design. Revit is really good for construction, is kind of how they break down. So we use Rhino really heavily. We'll interface with Revit with our designer of record, architect or engineer of record. But then and then from there we'll use a couple of different rendering engines. This one was done in V-Ray, and then a whole lot of Photoshop on top of this. So this is where the art comes back in, as being able to sort of integrate entourage, the people who are walking across here and the trees, and get sort of a particular mood for that image. The hand sketching stuff, I'll do this in notebooks. I've got like 4 open on my desk right now. I also do a lot of work on my iPad, which enables me to sort of send sketches to my drafting team and other engineers within the company very quickly, because I don't have to scan it or take a photo of it and email it. I can just send the digital copy. So the iPad is really good for that. And then in terms of analysis, we use a couple of different tools. There's a tool called, sort of a very industry standard tool called Resa, which is great for structural analysis for buildings. It doesn't do complex form particularly well. So then we also use a program called Caramba, which integrates directly with Rhino. And actually, let me flip over to another project real quick.
And did you learn those programs on the job or through your schoolwork?
Yeah, so Rhino, I learned in grad school. This image is taken from the Finite Element Modeler, which is Caramba that I referenced. I learned this a little bit in grad school, and then really, kind of figured out how to use it professionally on the job. This was something that, that was became more directly part of my workflow with Ender Studio. And even with this type of stuff, so it's one of these things where nowadays, like if I see on somebody's CV, if they're looking for a job, if I see Revit for our company, that doesn't really mean very much to me. But if somebody can model in either SketchUp or Rhino or 3ds Max, I'm like, okay, well, you'll be able to pick up Rhino even if you don't know it already.
Wow, so those are skills you're looking for particularly.
Absolutely.
And someone was asking if there are classes on those programs, and another person was asking if there are apps they can buy. Maybe if you have a link to some of them that you could put in the chat, that might be interesting.
Yeah, let me jot it down real quick, and then I'll throw some comments in the chat as well. Yeah, so the classes, definitely you can take classes. These days, if you want to learn how to do anything, YouTube is really your best friend. Like you don't need to take a class in CAD or in a modeler. There are things that you get by going through an AutoCAD class or going through a Revit class, going through a Rhino class. But in many cases, you can sort of pick these things up as you go. Most of you guys in this class are probably pretty digitally savvy, even if you don't think of yourselves that way, you can pick up software really quickly. So this is something that it's like, if you didn't have any modeling experience, that wouldn't necessarily be a deal breaker. It just, we would have to consider like how you can integrate immediately, right? But yeah, it's something that's worth kind of paying attention to, even in engineering, is not only understanding how you do analysis and work with analysis programs, but also how do you just model? How do you make, complex geometry? It can become very important.
And this image you have here is showing stress areas in red.
Yes, that's exactly right. So this is a house that I'm doing down in Big Sur, and I was kind of going to close with this one because it's an integration, and our role is all the way through the project, from sort of inception all the way to the end of construction, and it's all digitally integrated. So this is that plugin Karamba, which is a finite element modeler, which basically, what it does is it shows what you're seeing is stress. So you're seeing tension and compression in these individual units for this very complicated sort of urchin-shaped house. And the challenge, though, is that the model itself is not where you can end. And this is where your engineering, all of your engineering coursework about learning about codes. So if you get into, civil engineering or structural engineering, you start getting involved in, learning about concrete and steel and how it's actually codified, which is a little bit different than how you analyze something. Then you start getting into things like this, where we're taking all that stress information and we're doing, these are what are called interaction diagrams. This tells us what a given reinforced concrete section will take. And this is because the reinforced concrete section is both concrete and steel. And so we move from that, and this gets to be pretty computationally heavy. So again, coding classes also useful for engineers. It's something that's good to understand at least the basics of how scripts are written, how code is written. So we take that stress information, this is literally translating it into a heat map of whether a section, a given reinforced section, is overstressed or not. That moves into sort of a smoothed, this is through an optimization process where we're smoothing this out into a very limited number of concrete sections, because we don't want to have 30 different types for the contractors to get involved in. And then I'll just kind of blow through these really quickly. The interesting thing about this is that it's a concrete building, so we have to have formwork, and that formwork is also something that's too complicated to just hand somebody a set of plans and be like, build this. The geometry is, every part is unique, and the geometry is super complex. So what we did is, with a reinforced concrete project, the joke is that you have to build the building 3 times. You build it once out of wood for the formwork, you build it the second time out of steel for the reinforcing, and then the third time is the concrete itself. So here the interior formwork of the dome is going up. This is sort of the digital system of every piece of the mold that we're designing, and so we're heavily integrated all the way through the construction process. Every part is labeled and CNC milled and then shipped to site, and then we give them information on how to place those individual elements. And so here we've got the interior formwork in the interior of the dome, and then our reinforcing steel. And this is maybe just sort of interesting. I'll throw this in really quickly at the end. This is a prototype of that wall section. So when you do something really complicated, a lot of times building departments are sort of like, we have no way of assessing this, so go ahead, but you have to prove to us through a physical mock-up that this will actually work. And so this is us testing the construction methodology to see if we can actually get this thing to, to build, if we can actually do it. And then this is, this is what it looked like a few months ago. So we're
and who wants to live in a sea urchin? Who is this person?
Yeah, she's pretty eccentric. So this is hopefully this will at least partially answer the question as we go back here. This is what the interior space would look like.
And those are all windows, right? On the outside, yeah.
Everything is opened on that side. We actually, so the geometry is shifted so that the openings are big on one side and small on the other. And so we have the sort of maximum views from this side. And the site is just spectacular. I mean, it's a remarkable place. But yeah, the client is she's a character.
Yeah. Well, I want to thank you, Dave. It looks like Phaedra has joined us.
Yeah.
So I want to give her some time to speak as well.
If you have any questions for me.
I didn't hear what she said.
Oh, hold on. Let me mute actually. So we're sitting right. No. Oh.
Oh yeah, you're echoing now. Okay, now you're both muted. Yeah, so Dave, if you wouldn't mind typing in some links for some of that software so our students can maybe connect to it. And we want to thank you. This was really exciting to see these types of projects and to hear about the kind of work you're doing. So thank you so much for sharing that with us. And I think it's really interesting for students to also see, you know, where an art and civil engineering degree can lead to. So very exciting. And Phaedra has joined us. Can I tell them your relationship or? Yeah, so Phaedra and Dave, I think, met at Cabrillo and are married. Yeah, there's Dave's hand in the back, and she is a civil engineer who went to Cal Poly, but her specialty is geotechnical and structural, so a little bit different from Dave's. And so Dave was telling us, you know, about the work he's doing. Maybe you could start telling us about how you got to where you are now and, you know, like what you're working on, what kind of work you do. That would be great.
Thank you, Pretty. Oh, wait, Dave has to mute.
He is muted, but there's still an echo. I don't know.
Oh.
Okay, it's gone.
Hold on.
I think you got muted again.
Okay, technical difficulties. Now we're here.
We're good.
Okay. I just need to figure out how to share my screen.
The little green arrow at the bottom.
Oh, I see. Okay. I don't use Zoom. We use Microsoft Teams. So we're everyone's using different programs now. So I actually may know a few of you. And I actually taught at Cabrillo in 2017 and 2019, the surveying class. So I might recognize some names up there. I don't see everyone's name, but if you know me, say hello. Hi. So let me share my screen.
And Phaedra, you're working on a tunneling project, right?
Oh yeah.
I just told them about the tunneling project before we started into these speakers.
Yeah, that's a really awesome job. And one of the things that always makes me crack up about that job is there was that one movie, Ocean's 11, I think. They had maybe it was the 12, where there was a scene where John Cheadle was drilling with the tunnel machine. And that's not true, because the tunnel was actually drilled into the ground, and then they drove it off path, and then they just left it there. Sometimes in tunneling, it's cheaper to leave the machine in the ground than it is to remove it. So there's no way that they would have had that machine in that movie. So, you know, just some.
Oh, wow. That's a great fact. Thank you.
It's a hard thing when you're starting to watch movies and you see like little facts.
Oh, yeah.
That's not true. But it is a really interesting. And also, if you watch that movie, make sure you see how much room and space he has in that machine. You never have that much room or space. Think about like underground crawl space, you know, and especially like you're kind of roughing through the crawl space. That's pretty much what it seems like in at least small tunnel boring machines. So, but yeah, so I'll just go start out where I went to school and where I'm at now. So I started at Cabrillo, just similar to Dave, and studied civil engineering, and then transferred down to Cal Poly myself. I spent about 2.5 years at Cal Poly, and I had my focus was a little bit undetermined, but I knew I liked dirt. And I knew I liked doing something a little different, like a little weird and kind of off the beaten path. I thought for a while maybe I'll be an underwater sea, like a sea inspector for welding, and I had all these ideas. But then when I was at Cal Poly, one of my professors asked me what I was going to be doing after school. And I said, I don't know. And he said, I know a guy. And so I was literally in the room in his office, and he just called my old boss now, and said, I know someone who'd be really good. You work in tunnels. She wants to do something unique and something different. So do you have a space for her? And he said, yeah, send her on over. So I drove up to Seattle and got the job, and pretty much on the spot. And it was a real blessing, because that's really, I would say, how I got into tunnels. And tunnels are unique, and they're very specific. So there's not a lot of schools that you can study under tunneling, at least in the US. There's 2 or maybe 3 in the US that I know of that have more mining degrees: Colorado School of the Mines, Virginia Tech, and University of Arizona. And those are all 3 really good schools to study tunnels and mining. But most of the other schools are international. I mean, there's a lot in Norway and Switzerland and Italy. There's some of the best tunneling programs in Europe, for sure.
So did you learn tunneling just on the job, or did you
Totally.
go to school? Really? Wow.
100%. I knew close to nothing about tunnels. And so it's one of those industries that you just get joined up with a couple people, and you learn as much as you can by watching other people build and just glean whatever information that come before you. It's kind of a strange industry in that way, because that means anybody can really get involved in it. And I just want to show you the reason why anyone can get involved in it in terms of engineering is because it has so many different facets to it. It has civil engineering, mechanical engineering, electrical engineering, water resources, transportation. There's so many different types of tunnels out there that involve all these different engineering sectors. And so, like, for instance, like road tunnels. I'm sure we've all driven through road tunnel before. Train tunnels, they're still making train tunnels and still retrofitting train tunnels, especially on the East Coast for double stack trains. Sewer tunnels, something the general public doesn't even think about, which actually is part of the reason why I like it so much. It's kind of gives you this almost like a secret, like this inner workings of how the world works around you, and no one else knows or no one else thinks about. And so it's just, and you need it in order for the society to really have clean water and water resources, like clean drinking water tunnels. One of the sewer tunnels I'm working on in DC is to clean the Potomac River. And the Potomac River is one of the most dirty rivers in the United States. Actually used to be a swamp. And it was all along the tanneries. We're all along the river there in the 1700s and 1800s. And all the way through, I think, 98, it was one of the most dirty rivers in the US. And it was required by the EPA to clean it up. And they were on a consent decree, which means you have to clean it up within a certain period of time. And now we're at 2020, and people are now swimming in the Potomac River because it's cleaned up so much. And so in an environmental view, like, there's so many different ways that tunnels can be incorporated into cleaning our environment too. One of the things that people kind of don't know about cleaning the environment is like hydroelectric tunnels. There's like a lot of controversy with, like, yeah, it's green energy, but is it like good for resources, natural resources? So, I do struggle with some of those topics, and I try to look at projects more like objectively, just to make sure that it does fit within what I think, and then also like what is best for the society. Electric line tunnels, those are pretty like subways. Those are all over San Francisco. They're all over the world. There's new subways going up everywhere. China, Japan. I mean, some of the best in the world are in Japan. Just fantastic tunnels. Wineries have great tunnels up, especially in Napa. If you get a chance to go visit one, I recommend it highly. You can control your environment. It's like this perfect setting. It's kind of humid, but still moist and damp, and so you always feel you never feel like super like hot in a tunnel. It's like always the perfect temperature. So that's something that's always kind of fun to know. Mines, if people are interested in mining, caves, pedestrian tunnels, and culverts. There's so many different, and you know, there's probably a tunnel going under us right now and we had no idea. So the machinery and technology has gotten so good that there's so much that we would never know in a lot of ways. There's just
in some projects, I think it was in LA, where they were trying to put subways in and then the ground was sinking and stuff. Like, it doesn't always go so smoothly, right?
No, it doesn't. Are you talking about the purple in LA Metro? The purple one? Yeah. So LA has another, the big thing about tunnels is it's solely dependent on the soils, right? How you're excavating and the soils that you're in. And so, for instance, like this photo on the bottom right, you see these like really large it's a really large water cavern. And this is in Chile, and it's, and that's rock. So like rock is really sound and really stout. And so like the big buildings that are above it can withstand some of that stress because the ground's not moving underneath you. But where, if you look on the top right, see that's a cut and cover where they had to put it, had to put the box culvert in and open it up because it's pretty shallow, but also it's really soft ground. And so anything, if you tried to tunnel under that, it would, whatever would be above it would fall in. And soft ground is the worst. So soft ground and water is the worst for tunnels. It just is horrible. And LA has a problem with the tar pits, the tar sands. And I'm actually working on the LA Purple Line project, and you can see, I wish I had a photo of it, but you can't take a camera down there because it's has so much sulfur in it because of the tar sands that it could explode. So interesting.
Wow, interesting.
But you can see tar oozing out of the supports. It's phenomenal. And actually, I don't know very many people who've had the chance to work on a project like that before. It's kind of a very unique, very interesting area. They even found a saber-toothed tiger in one of the excavations for a station at Koreatown.
Very cool.
So look for that next time you go to LA and you're going to take the Purple Line. It won't be done for another a year or so, but that is they're going to put it on display. So it's right next to the tar pits.
Someone asked about the catacombs under Paris. How does tunneling factor into that, into maintenance of that?
So I've been there, and so Paris actually has some of the best tunnels in the world. Paris was the first modern sewer, and you know, don't just stop at the catacombs when you go to Paris. Go to the sewer museum, and it is a live sewer that you can go walk in the tunnels and go to, and it is phenomenal because it was one of the first of the kind of at least human technology of our history. And so the catacombs kind of fits in that as well, where you should go and just observe, like, this is pretty spectacular. The catacombs are a bit deeper than the sewers, but it's pretty unique.
Okay, cool. Thank you.
I mean, you have to be, it's hard to be claustrophobic and be in tunnels.
Right.
So that's one thing that is always that always people I talk about. And also, I have a poll. Is it during an earthquake? What do you guys think? Is it best to be in a tunnel or out of tunnel during an earthquake? You guys do a poll?
Why don't everyone type into the chat? They usually type into the chat.
Okay, and then so think about it. Say if you're in this tunnel on the left, which is a driving tunnel and then a subway through it. This is and then we'll try to see at the end what people think.
Okay, I typed it into the chat.
Okay.
So for everyone to respond. I don't have the poll function here. I don't know why.
We'll move on, and then we'll see what people say.
Yeah.
So there's so just to kind of give you an idea, some tunnels are really huge. This is actually a picture of me on the bottom in a rock tunnel that we were blasting. And some tunnels are really small. Some of them have, most of them, almost all of them have concrete support. So this right here on the top right is a shotcrete machine. Dave showed you a picture of someone standing there holding the shotcrete, which is impressive, and they're very good contractors. This is a robot. And so if you're really good at video games, this is actually, they literally have a video game console and use it to spray.
So if you studied gaming through school, which means you did the gaming but not the schoolwork, do you have a job running this potentially?
Actually, yeah.
Really?
Oh, yes. Oh, yeah. Yeah, one of the guys that actually ran this was, has blind in one eye. But he was like a phenomenal shotcrete operator. And so we were, and he was really good at video games. And so this is what he did. And,
wow,
you know, it's impressive. There is a lot of really good work. A lot of good, actually unions are pretty good in the tunneling industry. The one on the top right is, those are tunnel segments, and those get, I'll talk about this briefly, but this concept is more done for a tunnel boring machine. So the bottom right is drill and blast, so using explosives, and the top right or top left is a tunnel boring machine. And then there's some liners on the bottom. We've got fiberglass liners. This is more for like materials engineers. Mechanical engineers for steel and flange, like flange designs. It's pretty impressive. So just a couple, I'm just going over three quick ways of doing excavating, you know, in a hole in the ground. One of them is blasting, and it's one of my favorites because it's so unique and different, and you don't get to, you know, hold dynamite very many times in your life, and it's safe. You have to make sure you're safe and doing it safely. So these are.
I think the question the students might have here is, do you get to do this hands-on yourself?
So I have many a times, especially early in my career. So I've been doing this for about 15 years now. And so early in my career, I was allowed to fill the holes and actually set off a charge, multiple charges. And I think engineers aren't as, it depends on who you work for. So like if you work for a contractor as an engineer, you would be able to design and fill the holes and actually set off charges. But as an engineering for the owner, you really wouldn't be allowed to do that. But I knew someone who was working here, and so they let me do it. So, and there's really nothing like setting off a charge. There really isn't. I have a couple of videos that I wanted to show. And I mean, it's just such a, it's pretty exhilarating, and just, how am I gonna say it? This is just like a trim shot.
Were you there?
Yeah, but, and so it actually is just, it doesn't seem like a lot, right? That seems like that's just a trim shot, real small. But then the reason why it goes off at different times is because blasting, you want to give a free face to the blast. So this is actually not in a tunnel, but we did a lot of blasting. So this is a bridge pier along a railroad track, and there was actually a tunnel further down, and we couldn't interrupt the train service. And so when we had to get rid of this bridge pier, it had to fall on the opposite side of the tracks. So you design the blast in order for the slow motion, in order to have the bridge pier fall in the opposite direction of the tracks. It's hard to get videos of blasting in a tunnel because you're really not supposed to be close to it. But in this scenario, it's much easier to get blasting videos when you're outside.
That is so cool.
It is pretty fun. I'm not gonna lie, it's really a blast. Okay, the other one is a road header. So you know that movie like Total Recall? This is like very Total Recall-ish, very futuristic, but it's very effective. Some of the issues with this is you can only do it in certain ground types. It can be very messy, really dusty, and so a lot of them tend to put like a water spigot on the edge in order to like spray down whatever you're excavating. But usually this is good in like soft rock conditions. This is also really common in wineries because the machines are a lot cheaper than a tunnel boring machine. And a lot of places won't let you blast in the city limits. So even though blasting can be controlled. So using something like this would be good. I have a video of it.
Does one take longer than the other? I mean, this looks like it's small, so it'd take a long time.
Yeah, well, it does take a little bit longer, but not very. I mean, it depends on the ground entirely, and then how fast you are at putting up ground support behind it. So it's pretty dirty
and loud,
pretty messy. I mean, you have to be able to withstand some of that, but and so it's not always the best way of excavating. But this is kind of the cream of the crop. This is kind of one of the most common thing that you'll see on the news, at least, especially now with companies like the Boring Company who have a lot of marketing techniques. You'll see this. They're tunnel boring machines. This is where mechanical engineering and electrical engineering is really, really great, and definitely incorporates a lot of different types of engineering. This one of the companies that I'll put in the chat is a company called Heron Connect. It's a German company. There's about 3 different tunnel boring machine companies in Germany, 1 in France, 2 in China, 2 in Japan, and then 1 in the United States. And there might be a couple more sprinkled around, but those are like the main ones. Heron Connect, I think, has the best videos on their website. Basically what it does is it almost acts like a worm, I guess you could say, with a spindle on a head. And so the head rotates, and there's these disc cutters on the end of the head, and they score the ground in front of it. And as they score the ground falls to the bottom, and then it's brought up through a screw conveyor, kind of like a Da Vinci. Didn't Da Vinci design a screw conveyor? And you'll kind of see, like, as it's moving, there's these segments, concrete segments you can see on the right, that get installed by a conveyor belt. Get installed by a crane and set into place like puzzle pieces. So that's why it kind of looks like puzzle pieces. They're actually parallelograms, and that's how they like fit together. And so water doesn't come through. They put gaskets around them, and then they connect them with rods. And then in order for the machine to move forward, it actually uses hydraulic rams to push against the last concrete segment that was installed. These are really common in subways. When you're riding in a subway, try to look out the window, and if there's lights, you can see you can see these lines where the segments are. And then water tunnels tend to use these as well.
So does the whole thing come back out? Is that the idea, or does it go all the way through, or what?
It goes all the way through. You can't back up a TBM. So,
okay.
Yeah, you can like 5 feet, but that's about it. So. I'm going to show you, I'll send a video on how it works. There's Heron Connect has like a 7-minute video of how it works. And
that'd be great. I'll post that. That'd be great.
Yeah. It's really fascinating, and you'll learn a ton, and you'll get excited and want to work on those projects.
What do you do if you hit a snag?
What's that?
What do you do if you hit a snag? Like some iron ore, and you just can't get past it?
Are you talking about Big Bertha, the tunnel in Seattle?
Maybe.
Yeah, I think you are. So Seattle had one of the largest tunnel boring machines in the United States at the time. It was a 54-foot TBM, and it replaced one of the bridges that was there, the viaduct. They said they hit a steel rod in the ground. They did hit a steel rod in the ground, but that was not what stopped the machine. What stopped the machine was actually a bad motor. But there was a steel rod that they hit. So what you do is, in order for the ground to not cave in on you on the front, you need to pressurize the face. The same pressure, the same amount of water head and soil head that's on the front of this machine right here. Let me see how I do that. I don't know how to. I was going to draw. Oh, here we go. Okay. So there's water here putting against the head here, and there's soil putting pressure against the head, and it all wants to come through. In order to withstand that pressure, the machine has to actually apply the same pressure to the face. And so that actually has to be introduced adding pressure to the face here. And if you want to, you can actually, if you have something in front of you, you can actually keep applying pressure. One of the workers can get into a hyperbolic chamber, which hyperbolic chambers tend to be like right here. They're really tiny. And you go in there and you sit there and get pressurized, and then you can crawl through the face and cut it out. There are other things that you can do. If you're in solid ground, you can just see if you can open the face and have no material come in, and then go in and cut it out. I mean, there are some amazing people who work in this industry who get themselves into pretty tight situations, and it's tough, and it's a lot of money if you hit something. And so a lot of work goes into designing your alignments, designing your shafts. Everything goes into making sure that you don't hit anything, or you hit good ground, and you don't have to improve the ground as you move forward. So all the work that gets done ahead of time, which is millions and millions of dollars, is like to try to not hit anything and to not cause issues. So it's a very good question, though.
What do you mean when you say get pressurized?
So
like
it
a
actually
person getting pressurized.
It's so like diving. Like, have you been like scuba diving?
Oh, okay. I see what you mean. Yeah.
And you
No, I haven't, but
when you go down, you kind of slowly go down and constantly like push out your ears. Well, like you can do that in a vessel. Yeah. But and then when you come out of the pressure, you have to depressurize as well. It's a very expensive thing to do. It's incredibly expensive. So people try not to do it. And if you don't want to do it because it's pricey. So I mean, this machine is highly complex. It's they're wonderful. I mean, like I said, the one in Seattle was 52 foot in diameter. I think the largest one in the world right now is Switzerland. I think they went 55. There's always a race who can get the biggest machine. And so I mean, these are huge. These are like 5-6 story buildings tall.
Are they one-time use or no?
So no, they can actually be retrofitted. And they tend to be cheaper if you get retrofitted. However, no one wants to buy a retrofitted machine for a 50-foot diameter tunnel. If you're going to spend the money, I mean, these machines, I think the machine over in Redwood City, which is only 16-foot diameter, it was over $17 million. So one machine. And so that was actually, that was brand new. And then they are gonna bring it back to the company to get retrofitted, and it will be probably used again for another tunnel.
Do you foresee any of this getting cheaper, or will it always be like this?
That's a really good question. So I think it's the most expensive in the United States, mostly because of litigation. I mean, we kind of are a litigious society, and tunnels are no exception. I think there's a lot of risk that gets involved, and so a lot of the cost is actually built into risk. And so, yes, there are material costs. Yes, there's labor costs, and all that is going to be included in your bids. But a number, the multiplier that tends to make tunnels in the United States so high is the risk, and risk for. And right now, it's actually risk with COVID because people are working in close proximity to one another, and we've actually had some pretty horrible, COVID issues on our sites. Especially in LA. And then also working in these tight spaces, the city's structures up above you. I mean, there's a lot of risks. And then, you always get the lawsuit. There's always a lawsuit with someone saying that their doors don't close anymore. I mean, and a lot of times, we're not even tunneling near their house. And so it's like there's communities like hear about things, and, it's very litigious. And so that's what makes this industry so expensive. Wow. I don't think it's going to get much cheaper. There are new technologies that are coming out that will help, but I don't, at this point, I think things are going to just be more expensive.
Right.
So I'm just going to go through, I don't have a lot of time left. Oh, I don't have any time left. Can I go through just one quick project?
Yeah, sure.
Okay. So, I just wanted to talk about, this industry, like I said, is really diverse, for like what kind of engineering you want to go into. But, what makes it really fun is there's never a tunnel where you live, very rarely. So you do have to travel. And one of my coworkers who's just got into the tunneling industry about 2 years ago, he was really confused by this because he's like, I don't understand. Like I'm moving here, I'm moving there. And I was like, well, we go where the tunnel project is. The tunnel project never comes to us. And so if you are interested in travel, if you're interested in seeing new places, like this might be an industry that you'd be interested in, because there's always a project in the middle of nowhere that has a need for a tunnel. And although the Kaneohe in Oahu is not in the middle of nowhere, it's in this like really amazing place in Hawaii. And I got to spend quite a bit of time there and doing both the design and the construction. So this is a water sewer tunnel that used a tunnel boring machine, and it was done in rock and soil, mostly basalt, and it had this really beautiful like bluish green basalt and then coralline deposits. So you could see like coral layers. Geologically, it's fantastic. The length about 4 miles. It's a pretty small tunnel at 15 foot. It doesn't seem that small, but it actually is. When you get into those spaces, it's very small. It was round, over 800 feet of rock above you, and it had 3 shafts. So when I was talking about design, like, you know, Dave was talking about just like that planning. There's so much planning that goes involved in this. There's drilling, there's rock cores that you're going to get. When you just drive around, you're going to look at like the hillsides and the rock faces, and you can get so much information just by driving by and seeing a cut slope, because you'll see the joint patterns of where you're going to see from the surface are going to be the same joint patterns down below. So this is the tunnel alignment that we had. We had one shaft on the north side and one shaft on the west side, one shaft on the east side. It's between Kaneohe and Kailua, and it was a big mountain range in between them. So we used, there's the profile there. So if that's a plan view, so like bird's eye view, looking down the tunnel alignment, this is a cross section through that. And so you can see the 2 different shafts. One is on the right-hand side and one's on the left-hand side. These were used by like slurry wall concrete construction. It's a pretty standard way of building these out of concrete and reinforcement. And that's the slurry wall machine there. That's as me when we started excavating the tunnel boring machine. The machine is on the left-hand side, and then it left like on the right-hand side, you can see it like leaves this like really glistening rock. There's like a really heavy horizontal joint right in there. And then, you know, I was talking about the thrust, the rams that touch the back of the concrete segments. Well, this is a different type of machine. This is a main beam machine in rock where it doesn't have segments at all. So it just leaves rock exposed. And so instead of rams that kind of move the back, it actually has like little feet that push against the side of the rock and then move it forward. So it's like push and move forward. So it was a pretty neat tunnel. And I got to go to this great place and spend a lot of time. You do work long hours. I would say like 14 hours a day. You make a lot of money very quickly. But you don't have like during these jobs, it's hard. You don't have like a lot going on. You pretty much are on the job almost all the time. You do get breaks afterwards, of course. And then whenever you do get a break, I mean, you go out and try to explore as much as possible.
Someone asked if you ever get sick because you're down below, get sick in the tunnel.
I've gotten sick and never drink water that comes out of rock in a tunnel. I'm just throwing that out there. That was the sickest I think I've ever been on a job site. Yeah, that was the horrible thing. So that was a mistake. So yes, I have gotten sick. And yeah, you know, if you're sick, you try to get into work if you can, but you don't want to make others sick around you. And so you really try to be cognizant of that. And you are working in tight spaces. You know, I've worked all over the US at this point. Worked in Alaska, worked in Hawaii, I'm working in DC right now, working in Alexandria, Seattle, Washington. I used to work on the railroad lines, so I used to work all along the railroad tracks and railroad tunnels. So it's a very like travel friendly profession.
Yeah, we kind of have to go, but you were going to tell us, because there were a lot of guesses on the earthquake and tunnels issue, and I think majority of people said inside. Or actually,
Okay.
I only have 4 or 5. Yeah, 6 people say inside, 1 person says outside, and 1 person qualifies inside as being depending on what tunnel.
I would say the last one's probably the best answer but it's actually safer to be inside a tunnel during an earthquake. So when someone tells you when you're riding BART, oh, I would hate to be on an earthquake in BART, they're wrong. You want to be in a tunnel in an earthquake because it's round. And when it's round, it actually moves with the whole ground. So you actually may not even know that you're in an earthquake. There's nothing that can fall on you inside of a tunnel, and more than likely you will actually not even know. So unless these square culverts, that might be a little bit different, but in the round tunnels, that is the best place to be. Mostly because you don't have any. This is all in thrust. It's almost like the top of a doorway.
Right.
Like all the way around. So and it just is very structurally sound. And so this is the best place to be. And if you guys have any questions or anything, I know we're running late, but I can put my contact information and my LinkedIn. In terms of that LinkedIn question, I highly recommend getting a LinkedIn especially after you get out of school.
Cool. Thank you so much, Phaedra. This was great.
Yeah.
Thank you to Dave, too. It was great to have both of you on and to find you both not traveling right now. So I'll see you in a couple weeks. So let's thank them both. And this was really great hearing about all of this.
Oh, yeah. Oh, yeah. Here, I'm just going to put in the comments in the chat. Of the different websites, and then
that'd be great.
And I can even just send you an email to you, but
that's fine. And I think you were going to give me a link to a video that I could post to.
Yeah.
Herring or Herrick. What's the name?
Heron Connect.
Heron Connect. Okay, and while she's doing that, I know you guys, we've been going strong for 2 hours and 23 minutes, and it's without a break. So we are going to take a very short break, but when we come back, I'd like you all to have your project materials with you. So you will need paper, coins, 2 sort of blocks or large books, and a ruler. And then the last part of this class will be doing a project. A civil engineering project, and it relates to a lot of what we've talked about today. So let's come back at 6:30 and then we'll do the project, everybody. So now we're going to work on the project for the class, and for this I'm going to share my screen. And here we have, in this week's module, our project, which is to build a bridge from paper. There's a lot of background information available here on types of bridges, but the crux of the project is to use a sheet of 1 sheet of paper spread across 2 books that are about even in height, so that you can create a place over which to place your bridge, and to get at least 100 pennies balanced across your bridge. And so to do this, the procedure and analysis is listed here, and there is a follow-on discussion post that'll be due after class. And we're only going to take 15 minutes in breakout rooms to do this in groups of 3. And then we'll come back and we will share what we have learned. And of course, part of the project is to do a little additional work outside of class for this as well.